What's that? Nuclear waste recycled into diamond batteries with near infinite power. Well, that sounds totally legit and completely on the level. And they're scarcely alone either. How to turn nuclear waste into diamond batteries. New technique turns nuclear waste into diamond batteries. From Futurism Newsweek, diamond batteries created with nuclear waste may soon something or other. Nuclear waste could be recycled into diamond battery power. Nuclear waste turned into near infinite powerful batteries, and so on. Eventually, a highly powerful version of a diamond battery could power a mobile phone, James Barker of the University of Bristol's Faculty of Engineering told The Independent. Let's take a look at their promo video, shall we?
Nuclear power plants, though, invariably create nuclear waste, and therefore when any reactor is shut down, the waste must be safely stored and contained.
Correctamundo, which is one of the reasons no one has suggested, you know what we should do with that radioactive waste? We should concentrate it and refine it, make it millions of times more radioactive, then give it to people to use as batteries.
We then simply have to wait for it to stop being radioactive. However, this takes thousands to millions of years, making it a long-term safety and financial commitment to maintain and monitor.
Cool, so the radiation that they're talking about here is the graphite that you get in reactors, which gets a bit irradiated, and some tiny fraction of that natural carbon, which isn't radioactive, becomes radioactive carbon-14. So it's only modestly radioactive anyway, and further, those particles that the radioactive carbon gives off don't go very far. So the graphite is pretty much the safest storage form that you can get for that radioactive carbon that you've got already. You almost just stick it in a hole in the ground and there's nothing that can go wrong. It doesn't evaporate into the air. It doesn't dissolve in water. It's going to be there for the long game.
Because of our use of graphite moderated reactors, the UK has created almost 95,000 tonnes of radioactively contaminated graphite blocks.
What was it? 95,000 tonnes. Let's see, the density of graphite about 3 tonnes per cubic metre. So that's 30,000 cubic metres. So basically, it's a solid cube of graphite about 30 metres by 30 metres by 30 metres. The sort of thing that you could bury in the ground and forget about, seeing as graphite doesn't dissolve in water, and of course, the beta particles given off by this stuff have basically zero penetration. Basically, radioactive graphite isn't a problem, and only a tiny fraction of this is going to be radioactive carbon-14.
Recently, scientists from the University of Bristol's Cabot Institute have demonstrated that the radioactive carbon-14 is concentrated on the outside surfaces of our graphite blocks.
Okay, that's not unexpected, but fairly interesting.
By heating them, much of the radioactive carbon is given off as a gas, which is then collected. The remaining graphite blocks are still radioactive, just less so, meaning that they're less of a problem and less of a cost to deal with.
Okay, that's fairly interesting, I guess. So the total amount of radioactivity isn't affected here. It's just rather than burying a 30-metre cube of graphite in the ground somewhere, which is mostly harmless, you're going to concentrate it such that, I know, it's only a 10-metre cube of graphite or something that's about 30 times more radioactive.
The radioactive carbon-14 in gas form can then be converted at low pressures and elevated temperatures to form a diamond.
Cool. Chemical vapor deposition diamonds. Yeah, that's fine. You can do that. It doesn't really improve the safety of the storage of the radioactive material, but yeah, you can do that.
Our diamonds, though, are made of radioactive carbon, and so are able to provide their own energy to generate a small electrical current.
It's a beta voltaic. Basically, you get something that's kind of similar to a solar panel, and you're irradiated with nuclear radiation, and you get a minuscule amount of power out of it.
The carbon-14 will eventually turn back into normal carbon once its extra energy decays away.
No, it won't. It will decay and turn into nitrogen.
The carbon-14 will eventually turn back into normal carbon.
Seriously, how can you put so much energy into such a glitzy promo video without at least fact-checking it against, I don't know, say for instance, Wikipedia?
This gives us a nuclear-powered diamond battery. For this to be used safely though, another non-radioactive diamond layer is formed around the radioactive diamond, completely absorbing all of the dangerous radiation.
Cool, so all we actually had to do to make our entire graphite waste in the UK safe was put a minuscule layer of shielding around the outside.
On the outside, only a tiny amount of radiation can be detected, but this is less than what a single banana emits.
Nah, you started out telling us how dangerous all this radioactive waste was. Now all of a sudden, we have the most minuscule coating on the exact same radioactive nuclei, and we can turn the entire of the nuclear graphite waste of the UK and make it safe.
Active diamond layer is formed around the radioactive diamond, completely absorbing all of the dangerous radiation and converting it into even more electricity, making it near 100% efficient.
I'm gonna have to push extra doubt on that one, boys. I think you mean more like 1 or 2% efficient, which honestly, for those who have realistic expectations about this sort of thing, isn't so bad. But nearly 100% efficient. Gonna need to see some proof on that one, boys.
There are no moving parts, no emissions, and no maintenance, just direct electricity generation.
Wow, no moving parts, just like, say, for instance, a normal battery. And no emissions, like a normal battery. And direct electricity. I think you're saying it's a battery.
And since diamond is the hardest substance known to man, no other material could easily offer any more protection to the radioactive carbon-14.
Odd. I thought diamonds burned fairly easily, releasing all of that radiation which you've so wisely, massively concentrated into this battery. In which case, the battery would produce something like a fatal dose of radiation, killing you by acute radiation syndrome in about a week. And for anyone who's kind of confused as how can this stuff both simultaneously be almost harmless and really lethal, when it's on the outside of the body, these particles don't go very far. In fact, they'll struggle to even penetrate the skin. However, if you dissolve them and get them inside your body, then you get the full whack of that radiation. So these particles, which are almost harmless outside of your body, if you get them inside you, they become pretty nasty. Not that I want to be too harsh on these boys, because honestly, eating most batteries won't do you much good. But the carbon dioxide that you would get off, say for instance, burning one of these diamond batteries and dissolving water would taste like regular carbonated water. Kind of bubbly.
As we mentioned, the radioactivity of carbon-14 halves every 5,730 years, meaning our diamond batteries have an incredible lifetime. They would only reach 50% power in the year 7746.
Sorry, I'm just going to have to stop you there and call bullshit at this point. Now, normally I'd cut these guys some slack, because let's be real, the press would never take something and completely sensationalize it and blow it out of proportion, like taking every glitch in the noise of a clinical study and turning it into a potential cure for cancer. In this case, though, these guys have pimped their stuff out pretty hard, so I've got limited sympathy for them in the way that they've actually sort of stoked these flames of disinformation so hard themselves. And just so we're clear, Bristol isn't unique in this. Remember Berkeley, one of the world's top universities promoting the water seer, a clear scam that could be easily shown with the most rudimentary knowledge of physical chemistry to be a scam. And eventually, after a few years, that morphed into selling a $100 Chinese dehumidifier that guzzled power for $1,000 as a free water from air device. Yeah, no tears were shed when they went bust. Or NASA putting out all that crap about arsenic-based life and extraterrestrials, which again I called bullshit on day one. Yeah, that turned out to be crap as well. So why is this bullshit? Well, almost any way you look at it, and it's a shame that we don't have a scientifically literate media who might actually be able to explain some of why this is bullshit, or at least do the most basic calculations. But cool, let's start from the beginning. Let's assume that everything they've got here works as stated, that they get a bit of radiation and they turn it into a battery somehow and it magically works. Let's take a look at the best of what they got so far. A Russian design of a 2-micron thick layer of nickel-63, which is ludicrously expensive, by the way. I mean, I've worked with these. I've worked with stable isotopes of nickel. I think they were retailing at, $70,000 a gram, that sort of thing. Anyway, they're only dealing with a 2-micron thick strip of it. 10-micron layer of diamond on top of that produced an output of 1 microwatt and a power density of 10 microwatts per cubic centimeter. Cool, so a cubic centimeter produces about 10 microwatts, which would, given the density of carbon being about 3 grams per cubic centimeter and nickel, 7 or 8 grams per cubic centimeter, so that sort of thing. How many of those would you need to run a mobile phone? Well, a mobile phone runs through about a 5 watt-hour battery in about a day, which 24 odd hours. So it runs at about 0.2 watts, or 200,000 microwatts. And our few gram battery, how much power did that produce again? About 10 microwatts. So you would need about 20,000 cells like this to power a mobile phone. That battery would weigh about as much as a petite girl, about 60 odd kilograms, and would have a truly frightening amount of radiation locked up in it. Plus, you might remember the costs of isotopically enriched substances like this. Now, the good thing here is your 60 kilogram battery here would be expected to last your lifetime. Well, not entirely. So the nickel-63 here has a half-life of 100 years. That basically means it's the amount of radiation it gives off halves every 100 years. Carbon-14, the stuff they're proposing to use here, has a half-life of about 5,000 years. It releases its radiation 50 times slower. So it's going to generate about 1/50th of the power here. So to power your mobile phone, you're going to need something about the size of a small car, some 600 odd kilograms. And this is being exceptionally generous. So how would such devices work? Well, they're kind of the same as solar panels, except with solar panels, you've got some sort of semiconductor material and you're irradiating it with photons, light-type energy photons, to stimulate a voltage difference. Here, you're doing exactly the same, except you're irradiating it with nuclear radiation. Now, this isn't a minor difference. I mean, let me just give you the rough benchmarks here. Pretty much everything that you can see is held together by chemical bonds. Almost all of those chemical bonds have comparable strength, a few electron volts. So the visible spectrum has energy levels of about 1.5 to 3 electron volts, barely enough to break a chemical bond. Indeed, this is one of the reasons why when you get up to the higher end of the ultraviolet, it starts getting harmful, because you're now into bond-breaking type energies. So how much energy do you get out of a typical beta decay of a carbon-14 nucleus? About 50,000 electron volts, maxing out at about 150,000 electron volts. Enough to break about 150,000 chemical bonds. And this is one of the reasons why radioactivity is pretty nasty stuff if you don't know what you're doing. Now, this is also one of the big challenges in that anything that is subjected to these large amounts of energy gets the structure smashed up on an atomistic level pretty well. And this is one of the reasons why storing high-level radioactive waste is tricky, because each decay event that happens smashes up about 1 million nuclei in the structure. So from what I recall, it's the recoil of the nucleus that causes the majority of the problems here. So if you get a beta decay firing out of a nucleus, conservation of momentum means that both of these particles have equal momentum. And it's the heavy nucleus smashing up the local structure that does a lot of the damage. Meanwhile, the electron has an equal amount of momentum, but it's dissipated over many collisions. So those tend not to be as damaging. And of course, you've got to bear in mind that the more stable version of carbon is graphite. So the expectation is that if you smash up the diamond structure enough, eventually it'll turn into graphite, the more stable form. So each decay event that we get smashes up about 50,000 chemical bonds. So after 1/50,000th of this sample has decayed, you expect it to have mostly transitioned to something that looks more like graphite. And we know that roughly half of the nuclei decay in about 5,000 years, so if we just do a linear approximation, we expect that this thing will be mostly graphite after only a fraction of a year.
As we mentioned, the radioactivity of carbon-14 halves every 5,730 years, meaning our diamond batteries have an incredible lifetime. They would only reach 50% power in the year 7746.
Now, when it comes to claims that this battery will lose half of its charge over, say, 5,000 years, this is as bullshit as it comes. You see, when carbon-14 decays, it turns into nitrogen. I mean, let's just ignore all the recoil problems that they've got, right? If the diamond is meant to be an integral part of the structure and functioning of this device, well, newsflash, after the first half-life, which will admittedly be some 5,000 years, half of the carbon will have turned into nitrogen. It will have certainly lost all of its physical properties long before that. In fact, if this is actually required as part of the semiconductor structure, it'll start losing its performance from day one. Without some way of venting the high-pressure gas that's going to be coming off this, congratulations, you've just invented the world's first radioactive exploding battery. Now, some of the articles that I've come across do actually point out that this will only become a problem after hundreds of years. But if that's the case, why does their promo video claim that it's going to run for thousands of years? Look, I agree, a runtime of 50 years would be impressive and useful for some very low power applications. But that's not what you're claiming here. You're claiming that it's going to run for 5,000 years and make almost no mention that it'll only be able to power exceptionally low power devices. Incidentally, this is one of the battery's long-term problems. Pure carbon-14 is pretty highly radioactive. Now, they're right that it's harmless enough in diamond form because these beta particles just don't have that much penetration. But honestly, it's almost as harmless in graphite, like if you would just bury it in the ground or something. However, if it goes to a garbage disposal and you've concentrated all of your carbon-14, when that diamond or graphite is burned, it's dumped directly into the atmosphere. These are not and will never be sort of casual use type batteries. Next, we come to the practicalities, the penetration depth. Well, the beta particles, the electrons, the high-energy electrons that come off this that are meant to irradiate the semiconductor, if they don't get to the semiconductor, they don't generate any power. So you get this sort of self-screening problem that basically the decaying nuclei have to be really close to the semiconductor that they're meant to be irradiating. So now this thing that, carbon-14 self-screens really quite effectively comes back to bite you in the ass because the maximum thickness of these things is going to be microns. Optimistically, the thickness of a human hair. In practice, these batteries are going to look like wafer-thin pieces of glass. Now, admittedly, you might have to stack them up for sort of structural integrity and all that sort of thing. So they're right when they say you really won't need much shielding around this thing. But that shielding doesn't need to be diamond. Basically, shielding depends on effectively the density of the material, the electron density of the material to be exact. But anything that actually has comparable mass will be about the same. So glass would be about the same as diamond, would be about the same as alumina. There's really not any sensible reason to use diamond as a shielding material. Next, this thing will be screamingly radioactive. But it's diamond, I hear you say. And you just said that the new radiation can't really easily get out of it. Well, yes, this is all true. But if that carbon-14 gets into your body, then it becomes almost as dangerous as any other radiation. And it turns out that diamonds can be burned really fairly easily by any munchkin with a torch, like, say, for instance, myself. I'm burning? I think that's burning. There we go, one burning diamond. This is gold. My God, that's so cool. It's amazing. That's gotta do it. Come on. That's almost white. But on the bright side, it was a real diamond. And trivially dissolved in water to make the world's most radioactive beverage that would be almost undetectable and would be exceptionally dangerous.
At over $1,000 for this bottle, though, not even counting labor, I still wasn't sure if it was actually worth all the work and money. Tastes, exactly like soda water.
For certain, drinking a soda with carbon-14 dioxide would be fatal. So how much radiation do you actually need to kill you? Well, a fatal dose of radiation is about a 350 joule whack of something radioactive. So a gram of polonium-210 gives off about 140 joules per second. So that would be enough if you were to get in your body to kill you in about 2 seconds. Outside of your body, holding it in a little vial, it would be essentially harmless. But if you were to eat about a microgram of the stuff, you would have absorbed enough radiation to kill you in a couple of days. So let's take a look at how much of this radioactive diamond you would need to kill someone if you, say, burned it and dissolved it in their soda. Well, there's this article here that says it'll produce 3 terajoules of energy over the first 5,000 years alone. Wow, that's super impressive. That would be like 600 million joules per year, or 1.5 million joules per day, or 20 watts. 20 bloody watts! Yeah, sure, damn straight that'll charge your mobile phone. In fact, it'll charge 10 of them. But it's also enough radiation that if you were to get it inside your body, it would give you a fatal radiation dose in about 10 seconds. Yeah, I don't think these boys can do their maths properly. But what's that? You scroll up a bit and they say it's going to generate about 15 joules per gram per day. Okay, now we're getting into something sensible, which would mean that if you were to drink about a gram of this stuff, after about 20 days, you would have absorbed a fatal dose of radiation. But great, 15 joules per day. Now let's take a look at that and see how long it would take to charge your mobile phone. Typical mobile phone would have about a 2,000 milliamp hour battery and about 30,000 joules in it. 30,000 joules at 15 joules per day. Yeah, great. This 1 gram battery is going to take almost 6.5 years to charge your typical mobile phone. Then, of course, there's the problem with the expense. You might remember that I told you that isotopic enrichment is expensive. So the cost of the carbon-14 alone here, I mean, let's just take a look at current market prices. Carbon-14 is basically sold on activity. So 5 millicuries costs about $2,000 odd. So about 1/5 of a gram of carbon-14 gives off about 1 curie of radiation. So 1 gram of carbon-14 is about 5 curies, that sort of thing. So current ballpark prices, you're looking at about a 1 gram battery costing about $2 million. Or from earlier, our 600 kilogram battery to run a mobile phone would cost about $1.2 trillion. Now at this point, you can knock zeros off this almost all you want. I mean, let's just make it 1,000 times more efficient. You're still looking at $1.2 billion simply to charge a mobile phone. But let's cut them some slack here, because a lot of the problems with carbon-14 is that, first of all, most of the time it's sold in biological forms, which are actually fairly dangerous to handle. But let's be super generous and say that they can reprocess and do the isotopic extraction about as cheaply as you can extract carbon-13. So let's just give them carbon-13 prices for their carbon-14, which is about $400 per gram. And that is super optimistic. So, you turn this into diamond, you're looking at about $1,000 per gram. So what's that? $1 million per kilogram. So for a 600 kilogram battery, you'd still be looking at $600 million. Best case scenario. And somehow this crap gets reported in the Independent as nuclear waste recycled into diamond batteries with near infinite power. Thousands of tons of radioactive material could be used to power everything from pacemakers to spacecraft. So I hope you enjoyed that, man. If you did, sure, drop a like on this video. And of course, if you don't want to miss out on new uploads, make sure you hit the notification bell. And if you found this kind of cool and informative and want to support this channel directly, you can do it through Patreon or by visiting my Amazon store below. And as ever, thanks for watching.